Okay, we're going to try to learn a little bit about moisture today. So we're going to take a look at some of the implications from moisture. And let's see if we can start this slideshow at the beginning here. Uh, what is moisture? And with that, how does it impact stability? We're going to talk a little bit about atmospheric stability as well today. So the Earth has an interesting water cycle, and we're going to get into that with looking at atmospheric rivers. What I want you to notice is this cloud band right across the Pacific and into the northwestern almost United States. Pacific Ocean has a lot of moisture. So that is an atmospheric river of moisture, literally, stretching all the way from the Pacific across Asia into North America. That is a ton of moisture available to the cyclone that is developing along the west coast of the United States and will bring in a lot of the rainfall that they get. A lot of rainfall on the western part of the United States comes from these atmospheric rivers that develop over the Pacific Ocean with time. So here you can see it as it comes in, a depiction of it, and it rises up over the mountains. If the air is hitting a mountain and it's coming from towards that mountain, it's going to want to go up and over that mountain. Well, as it rises, it's going to produce rainfall and clouds. And they can cause a tremendous amount of flooding in these areas. So the total amount of water in the atmosphere actually is relatively small, and it's all confined into the troposphere almost. Very tiny little bit in the stratosphere. And if all the water vapor were removed from the whole globe, everything would basically get an inch of water over the world. And the water is continually entering and exiting. Well, here is a water cycle. Think about it. Over the open ocean, you have the sun beating down, and you have evaporation going on. That pulls moisture into the air. So air that moves over an ocean or over a body of water is going to get moisture with time. Over the Great Lakes, when you have air moving across them, especially in the wintertime, the sun beating down there on the Great Lakes is still maybe 40 degrees. The air above it maybe 20 some or less in the wintertime. There's evaporation going into that air, so it's adding moisture to that air. Now, what happens eventually? Clouds and precipitation form. Some of that rain comes back, or precipitation, maybe snow, comes back over maybe the lakes, maybe a river, maybe the ocean. However, other parts of that will go over mountains, occur in a city, for example. And all of these has different transfers of the water then. So say you have snow on the top of the mountain, out in the west, they love snow all along the Cascades, the Rocky Mountains. Why? Because snow melts in the spring and into the summertime, causing the rivers to flow more. And that water then flows down into where the population is, in the lower elevations. And it allows them to irrigate fields, develop agriculture out there. Without that snowfall, there is no agriculture. So that's why every year they look for tremendous snows in the wintertime in those areas. Now, what about an urban area? Some urban areas actually have pavements over all the area. What happens is the water has no place to run except into the sewer system there, a storm drain maybe. And if the storm drain can't keep up, which might happen in a thunderstorm when the rain's really coming down, you wind up with some flooding in these urban areas sometimes. Oh yeah, there's also the land. Say you have mountains, and in West Virginia you have lots of mountains where the water is going to flow down the hills and down to the valleys very quickly. The flatlands, on the other hand, the water will gradually be absorbed, maybe by trees, maybe by agriculture, maybe into the ground itself. Oh yeah, trees and plants have evapotranspiration. They have transpiration of water through their leaves back into the atmosphere. And eventually some of the water winds up in the groundwater where wells are drilled into it and all to tap it out. So you can see there's a complete picture of a water cycle within the atmosphere. And I'm interested in hearing your discussion of that for your area. Here are all the different potential changes. We have evaporation, condensation, transpiration, evapotranspiration. How about sublimation, where ice goes immediately into water vapor, into a vapor? And deposition. Precipitation is part of this. So we describe this moisture as humidity. And humidity varies from season, day to day, literally hour by hour. And look at all these measures of this. You're going to get a very brief familiarity with each of these. Vapor pressure. Well, water vapor is a vapor. So it has its own pressure. We've talked about air pressure in the last unit, and water vapor has an air pressure. The more water vapor, the more pressure. Mixing ratio. Well, we take the mass of water vapor for the mass of the remaining dry air. After you pulled all that water vapor out, you have a little bit of air left, maybe in a cube somewhere that you define. And when you compare the two, that's the mixing ratio. The higher the mixing ratio, the more water vapor there is. Specific humidity is just keeping the water vapor there. It makes a slight difference in the amount of water vapor and what that ratio would actually be. And absolute humidity is the mass of water vapor per unit volume of humid air. So again, these are just measures of how much moisture. The bigger the number, the more moisture is in the air for that sample. Saturated air can't hold any more. In other words, what's happening is that the air parcels are transitioning. The water vapor is condensing and evaporating at the same rate. So there is no change at that point in time between the amount of water vapor going into a liquid and the amount of water vapor from liquid water moving back into a vapor. However, changing the air pressure disturbs this and the air temperature. The hotter the air is, the more it can hold water. Why? Because it pushes the molecules further apart, so it has room to put water molecules there. And here you can see the curve where the temperature and saturation vapor pressure is. Notice it's pretty steady down in the low levels where it's ice. And then it gradually goes up, 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 and really gets relatively high. In the summertime, it can hold a lot more moisture in summer than it can in winter. Interestingly, and you're going to really look at this later when we talk about cloud formation, ice. The saturation vapor pressure is lower over ice than it is over water. The reason for that is ice molecules are not moving as fast as the liquid water. So that is a key point going to help in why we have clouds form the way they do. And while relative humidity might be the most familiar term, all it is vapor pressure over saturation vapor pressure times 100. So what it's saying is, okay, if it's 90% relative humidity, that means it can still hold 10% more water before it can be completely saturated. When the relative humidity is 100%, it can't hold any more water. And here you can see during the day, think about it, as the temperatures drop, relative humidity is going to go up. That's why we get fog in the morning. During the day, on the other hand, temperatures are going up. Even if no water is added, that air can hold more water, so the relative humidity goes down. Dew points are just another measure of water in the atmosphere. It's the most common one. What it is that the temperature drops to that point, to the dew point. There'll be dew form, so there becomes 100%. So no change has been made to the air. The dew point is the temperature at which everything will begin to condensate out. And here you can see the change in dew points on average between January and July. Notice in July, eastern part of Oklahoma and up into the area here, dew points get pretty warm. However, in the wintertime, they're quite cold, so it can't hold a lot of moisture. So the amount of moisture is very different in the air. And condensation produces clouds. It's a visible aggregate of tiny water droplets or ice crystals. So as the air cools, saturation vapor pressure decreases. Clouds begin to form. So if an air parcel is rising up into the air, it's cooling because it's rising. We know that. And eventually it gets saturated and vapor begins to condense, and we begin to see a cloud form. Now, this has an impact on atmospheric stability. Think about a balloon. If you release a hot air balloon, why does it rise? Because it's warmer. If it's warmer, air parcels are further apart. It's less dense than the surrounding air where air parcels are closer together. So when you send a parcel of air up, and I don't care what size that parcel of air is, if that air parcel is warmer than the surrounding environmental air, it's going to continue to rise, or it's going to be unstable. It's going to want to rise faster because it wants to get to somewhere where it's the same temperature as the surrounding air. So that's why it has to cool. So if we add moisture in here, what happens is that moisture begins to condense at some point when the air is cooled. So the air parcel, instead of cooling at 9.8 degrees, will only be cooling at about 6 degrees Celsius per 1,000 meters. What that means is that condensation, which releases heat, has caused the parcel of air not to cool as fast. So it may become unstable compared to the air around it. So that's why a lot of times, depending on how much moisture is in the air, as to whether air will become unstable. And the more unstable the air is, the faster the acceleration of that air parcel is in the vertical. And if you get a really fast moving air particle, that's when you get your severe thunderstorms. And here we can talk about the conditional instability. So some of the lifting processes are fronts that may begin to push an air up. Sun's heat actually will do it, especially in Florida. Warm fronts, cold fronts, terrain. The mountains of West Virginia, if you have air coming in from the west, pushes air up, you wind up getting heavier rain on the west slope of the mountains. If you have air coming in from the east, it's just the opposite. And then there's something called the lifting condensation level. It's the altitude at which the rising air becomes saturated and clouds form. That is going to be the base of thunderstorms. And you can see that there's rain shadows depending on the mountain range. So just quickly, I wanted to show you, here's a current weather map. Look at all the fronts that we can see on this, cold fronts in the eastern United States, another one coming down out of Canada here. And if you were to look at low-level water vapor, this is in about the lowest 3,000 to 5,000 feet. You see moisture coming up to the east side of that front. Now, if I change the elevation of this, and we go up a level to the mid-level, which is about 15,000 feet up, what I see here is a whole bunch of moisture, but the most of it is actually up here being saturated, more lifting there. But this is coming all the way up from the Pacific into the eastern United States. So you can see the moisture feed along this. The actual moisture and the rainfall that's occurring with this front has actually started out in the southern Pacific Ocean from the Gulf of Mexico and then on up into that area. So it's interesting how you can follow the flow of moisture into an area. So I hope you get a little bit out of this, and let me know if you have any questions.